is basically an accelerated learning cohort. An accelerated learning cohort is a platform where we typically work with learners, data science learners, to learn data science concepts from and data science tools from scratch. And now the data science tools and concepts and techniques are broken down into, various models, into there's an introduction to Python, introduction to NumPy, introduction to pandas, and now we're doing an introduction to data visualization. Right, so my name is Pablo. I am the founder, host, convener of the Data Science Mentor sessions. And this session is session 7. If you're watching this as your first recording, or you're seeing this, you're watching this as a recording, then it means you have access to our Data Science Mentor resources. And if you're watching this for the first time, it means you have to start from the first. You would almost always see, just to get my annotator working here, you would almost always see that there is the numbers here that indicate that. Right, so today we're going to be looking at histograms, billings, and density. And one interesting thing about histograms is one interesting thing is to think about the intuitions behind histograms, and we're going to use Matplotlib to plot a histogram, but would like it to be ideal to talk about why it's really really interesting, and then go on to plot one. Now, a histogram is a bar chart. So let me make this different. Let me bring this here. I make this a lot bigger. Then underneath, I can talk about histograms. Now, a histogram is a bar chart. So that's the first thing. A histogram is a bar chart. Right, and it is used to visualize distribution of numerical data. Right. One thing it does really well is that it groups data into intervals or bins, then shows how many data points are falling into each bin. So again, it's important that these things are stated. It groups data into bins, right? It groups data into bins, or that's what I call them, intervals, and shows how many data points fall into each bin. Right. So a few things that make a lot of sense about histograms are the bins, which are the different ranges or the segments of the data, the bars, which show the frequency of the data in each bins, and the shape. So the shape. So these three things are really important. So again, I'll look at them. So I'll call them key. I call them key pointers in histograms. Key pointers in histograms. Now the first will be bins, we just talked about them as intervals, right? So there are ranges or intervals, ranges or intervals. Then we would also look at bars. Now, these bars are heights, and these heights represent frequency of the data in these beings. So these are like heights that represent the frequency of the data, the frequencies of the data in each being. And then finally, shape. Now, the shape is important because it reveals the pattern of the data distribution. So again, it reveals patterns of the data distribution. And when we say patterns here, now we're now going to see skewness. We're going to see stuff like skewness. Is the data skewed? You know, do we have gaps? Do we have outliers? So these are kind of things that we get to see. Now, one really interesting thing is, you know, we always want to, you would use a histogram to understand data distribution. You know, is it skewed? Is it bimodal? Is it symmetric? Is it a normal distribution? Of course, you want to spot outliers, so you want to maybe check if you have anomalies or spot isolated information. And sometimes we can also overlay histograms to compare distribution. And we're going to be looking at this in a bit. Now, I like when I do this, one of the things I like to do is to use NumPy to generate random data. Then when we use NumPy to generate random data, then we start to do some visualizations. Then we start to look at parameters, like what are these parameters in it. So that's what I'm going to do to show us this. Now, again, I always start each session as if it was the first in the notebooks that are shared in the Google Drive resources. You would notice that they have great deal that we've been right, and the code book is comprehensive. So I start by I'll import matplotlib .pyplot as plt. Because I am going to generate random data, I'm going to import numpy as np. Then I'm going to, I always like to use a style. The last time I used, let me see, plt dot u dot style dot plt dot style dot available. Yes, and so this should show me a bunch of different styles that we can use for our background. So let's use this. Let's see if we can use this. Let's just use this for today. So we have this. So I'll just basically now say style.use. I'll have this here. It's just more like a setup for what we're going to be using today. Now, the next thing I'm going to do is I'm going to generate random data, and then visualize this random data. Normally, if you have followed, from the introduction to NumPy or numerical Python with data analysis, I would always start up by creating RNG random number generator, and I'll use np.random default, so random number generator, and then I would use I would just have like a seed, something that says, okay, reproduce. right? Then I can now go on to create data. And then this data is going to say, with a random number generator, let us generate samples. So it's going to draw samples from a normal distribution. And you can see we have lock, scale, and size. Now the lock you see is the mean, which is the center of the distribution. The scale is the standard deviation, and the size is typically, the size of what we want. Now, but if I choose not to put that, then we could just have like a default one. So let's just basically say I want size, and just let me use 1,000. Yes. Now, just if I run this way, you can see that this is what it generates. Right. So now I can now say PLT, and I'm going to just use a simple PLT plot, right? Without objects, just a simple PLT. So I'm just going to say PLT dot hist. Now there's an interesting thing. By the time we do CBON, we'll just start to see that we can also typically have a way to do different plotting, and then also make CBON. CBON is also a plotting library, but it uses matplotlib as a wrapper, right? So here I say, let's plot this data here, and then let me go on to say plt.show. So, right, so you can see what we have here. Now, the interesting thing about this very stuff I just did is by default, right? So by default, a lot of things are done, especially you can see that you can see the bins over here were basically decided for time, right? And then we can see what we have in here. Now, for you to tune your display, there's a lot of ways to customize it. So this is like by default what it is. So if you have numerical data, you can basically, see what the distribution looks like. Now let's try something else. Let's try and customize. So let's try and customize the hist plot, the histogram. So let's customize. Now, if we're going to customize the histogram, then we can say plt dot hist, and over here we can work with here. We have a bunch of things and we're going to use them, and as we use them, we're going to now start to say, okay, this is what it is. And you can. One interesting thing is I may not. Of course, I would not check out. I won't check out everything, but a few of the parameters I use, you can also test out your own parameter and see what it does. Now, let me put a question mark here. So we already have. You can see this is what we have here. So let me move over here and now say plt.hist. Now, if I was to come here, you see that we have X. Now, if I move down to the breakdown of the parameters, we say you see X is an input value. This takes either a single array or a sequence of array, which are not required to be of the same length. It's typically the data we're working with. So I can come over here and I'll put data. I won't typically just put X, I'll just put the data because it recognizes that that's the first thing. Now you can see that if I looked over here, you can see for the bins, we didn't indicate what bins are. So next thing I'm going to do is I'm going to say bins. And remember that if we come back here to this key concept, right, you can see over here that bins, ranges or interval, they are key pointers in histograms, right? So over here, I'm going to introduce bins, and then let me say 30. Now, if I come back here again, just look, you see over here, density. Now, if true, it will draw and return a probability density, which it will tell you, like it typically tells you, like, this is like what the probabilities are, and it will try to draw that probability in it will give the probability of the y-axis and to show you, okay, what's the probability that this has a chance of happening from, depending on the total stuff we have going on. Now, with that, I'll say density true. So let's get a probability density. Now, I also want us to see that we don't have a probability here. We don't have that set up. So I'll put here density, and I'll say true. Is there any other thing? Weight cumulative. Let me see some that we could use. We could try. Okay, let me say the histogram type, the type of the histogram to draw. So you can see that we have bar stacked, stepped field. The default is a bar. So the bar is a traditional bar type histogram. We have bar stacked is a bar type histogram where multiple data are stacked on top of each other. We have step field. There is a line plot that is by default field. So let's try. Let's look at his type. Yes, and with his type, we're going to use step field. Then, what else? We can also use the color. Yeah, color. We've also looked at color before. You can also look at color, and in color, there are lots of things we can use. Let me use steel blue. I use steel blue because I mean, I've used it recently while I was reading. There's a book I read to do so. Steel blue often just comes out. Let me see how it will. I just like the term steel blue. Any other thing? I think that's okay. I think that's fine. I don't think there's need for any other thing. Sometimes there are a few things that are inside this that I think they exist generally. I'm going to look at this stack. There's beans. Yeah. You can see. You see these guys. We can use this as this in future. I will talk about it. This quarks, this keyword arguments. But we have steel blue. Is there any other thing? So let's see what this looks like, right? And then we say plt dot show. What's going on function? Why am I not having? Okay, hold on, let me see. Okay, let's generate this. Let me come over here. That's weird. Is there anything we're missing out on? There's a data here, there's a bean type. There's a function, show. Oh, can you imagine? I nearly forgot that. Oh yeah, look at that. And so you can see we have like a probability density over here. You can see, and you can see that even with the 30, it kind of finds this still being ideal, right? Let me see. Let me see what 40 looks like. still, I think you can see the differences in their different, the ways they are changing over here. You can see how it's basically getting back here. So let's, again, let me take it back to 30, and you can see again, right? You can see very, very tiny changes, right? So there are things. So with PLT dot this, there are a lot of information, right? For instance, there's so much information. There is there is something we can use. Okay, let me try something else, right? Where we can now have different where we can have different visuals start. So they're typically, we're going to have this step, but they are going to have different like stats distribution on each of them. So let me try that again. This will be a lot interesting. So say that say that we have different data points, right? That we have numerical data points, and we're trying to visualize them on one point. So I can now say I say x1, and with my random number generator, I'll create a normal distribution. And remember, in the normal distribution, we had log, which is the mean, we had scale, which is the standard deviation, and we have size. So let's say I say we have 0 as the mean, and we have 0.8 as the standard deviation, and 1,000 of them, 1,000 elements. Then we have x2 here, and we have rng the normal, and here we have -2 as the mean. We have 1 as standard deviation, and 1,000. Yes. Then x3, here we have rng dot normal, and again we have 3 as the mean, 2 as the standard deviation, and 1,000 numbers. Now we have this. Now that was the interesting part where we introduced where we saw here, and I was going to talk about that, which is this. You can see quags, which are like other parameters that are typically there is, and this is like a keyword argument that we can introduce in many ways, right? So there's a lot that is being said. You have to take time out to read through them and see a bunch of things. For instance, you can see arrays. You can have a list of array, the values of the histogram being, you can see density and weight for a description of the possible semantics. If input X is an array, then this is an array of lengths, depend on looking at the bins. If the input is a sequence of arrays like this, then this is a list of arrays with the values of the histogram for each of the arrays in the same order. So which means we can just put, we can put an arrays, we can put arrays, or we can put like a data type that just has different elements inside, right? So that's one. What else can we do? There's something that isn't here, and I'm going to introduce that. I'm somehow surprised. I think it's often a general idea on why this is not always there, but I'll introduce it. So let me say, let me call this keyword argument, and inside I'm going to create a dictionary. And this dictionary, I'm going to have this dictionary in here, and this dictionary is going to have, I'm going to have like a his type, his type. Let me hopefully not miss how it is spelled. Okay, so a his type. So you can see that in a his type, I can basically come over here. the hist type, I would say, let me put it here, and inside I would call this the same thing I used here. I'll have to copy, because creating it as a dictionary would mean, it would mean that I will have to take this step field. Okay. Right, so I take it over here. Now, the next I'm going to do is I'm going to introduce something called alpha. I have used alpha a lot in the past. Now, alpha, what alpha does is transparency. So it creates a level of transparency. If you don't want it to be transparent, you can leave, by default, you can leave alpha without. But if you want it to be transparent, that like different distributions can be across each other, you can reduce alpha, let's say 0.3 or 0.4. Then I can say density. This one I can spell it. Density is true because we're going to see the probability density distribution. Then with bins, I can say 40. Then I have this covered. Now I'm going to go here and say plt.hist. And the first thing I'm going to have is I have x1, comma, and I can now put star quarks, because it's going to have different numbers of keyword arguments, an arbitrary number of keyword arguments. Functions, always remember that was a thing in functions. It's your first time taking this, go and check out, if you have access to the data science mentor program, go and check out Introduction to Python. There is a session for Introduction to Functions, and you see like arbitrary keyword arguments when you now use your asterisks. So just similar, that's what I have to say, similar. Then here I have 2 stars, and again with the quags, and then plt.hist x-tree quarks. Right. So we have this too. Now, I think then finally we should be able to do plt.show. Look at that. You can see. So you can see how that works. Now we have 3 distributions, right? You can see all the distributions we have, the 3 distributions, and this distribution. And you can see, look at that. You can see the alpha. If I need the alpha 5, you can see that it becomes thicker. All right, look at that. It now starts to look really nice, right? But you can see that it becomes transparent. And then by default, it uses red, green, and blue, which are the default colors. So this beans can be created this way, and it's so interesting how we can use it to check out 3 distributions, like 3 distributions of data. Right. Okay. So maybe I can try out one last thing. We can try out one last thing before we wrap up. So this one is just, this session is on histograms, and we can, should we? We can do maybe histograms and binings. So we can we can also have a 2-dimensional histogram, right? So when we have a 2-dimensional histogram, we sort of like find a way of dividing the number of lines into bins, and then we can now create a histogram that's in 2 dimensions, right? By dividing the points amongst these 2 dimensions, right? So we're going to create that, right, and then plot it, right? Now sometimes we typically want to maybe have a sense of what our distribution looks like, maybe in different ways. And And that way we can typically be like, okay, well, this makes a lot of sense. And that in that way that we can look at our data and see if there's something really interesting about it. Right. So this is just stuff. I think the use cases can be really interesting if we want to look at our data in many ways, right? If we want to look at our distributions in many ways and see if there's a form of a concentration in how this is visualized. Okay, so let me look at that and see. So here, call this a two-dimensional histogram. A two-dimensional histogram. And then we are also going to divide the bins. We're going to like kind of flip the bins too. So I'll say two-dimensional histogram. Yeah, two-dimensional histogram. That's one. And then we also try to see and put it down dash here, and then we can also look at bins. Yeah, we're going to generate data points for this. Right. We're going to generate data points for this so we can see how interesting that looks. Right. First things first, we'll create a mean. We have 0 by 0. Let's put a list 0 and 0. So these are two means we have. And we'll call this hove. Right. And typically we're going to see what all this means when we now use like a multivariate distribution to look at it. So here we're going to have 1, 1. Then we have another 1, and we have 1, 2. Now, the next thing we're going to do is we're going to say X and Y. And inside, we're now going to have RNG dot multivariate normal. Now, a multivariate normal will draw samples from a multivariate normal distribution, right? It's a different type of a one-dimensional normal distribution from one level to another. So that's why we're going to be using this here. And so what we're going to do is we're going to now have different levels of like a normal distribution. So inside of it, I'm now going to call the mean, and I'm going to call the covariance. We're going to create like a matrix. So we have one, like say, let's make it 10,000. And interestingly, when we do that, we can now do, we can now transpose it. So again, let me run this, and then we can see a sense of what this is. This is type. It's an array. So that means I can take X and look at maybe the first 10 features here. So you can see what the first 10 features look like. Then we can now go on to now say plt.hist and look at what we're using, a 2D histogram. And inside of it, we're going to have X and Y. And then we can now have bins, because it's important to look at bins. We could just set it at 30. Then we're going to now check out we're going to now create our color bar, right? So we just call this CB, and inside we have plt.colorbar. Where are you? So with the color bar, we'll add a color to our plot, right? And so that's what us to do. Now, we want to add colors to our plot, and we want to say cb.set underscore label, and we now call our color bar the counts in bean. So in the different beans we have, it's just it's going to show us our different counts in bean, and then it will do like a graduation of the colors, the different colors that exist inside there, right? Then let's see, plt.show, like that. So now you can see that if you look at it, you can see that the different distributions we have are being featured, right? And you can see that based on the different distributions from, you know, how they are visualized, and the darker it is tells you what we have over here. And you can see that the lighter it is, you can tell them in the different shades here, right? So to a lot, right? You know, it sort of like helps you, you know, visualize data in different dimensions, and tells you, okay, what's happening in one dimension over the other, what's happening in here. Like you can see that we have like different distributions depending on the kind of situation we have or the kind of data you have. If you have sensor data that come out and you want to look at maybe the distribution of the data in a different dimension, not just like typically in like one dimension, right? And you can tell, you can also tell that you know, depending on what you're looking at, you know, you can always tell if there's something interesting going on in these dark areas over here. So this is what like a two-dimensional histogram looks like, right? And yeah, so that's typically an interesting thing about histograms. And of course, just like we did, we also looked at their binings, because the binings are important. And we also at this point looked at density, which tells us, like, you know, the probability of, you know, the probability of having certain distributions show up. You can see this distribution over here. You see that the probability tells you it's high. You can see the chances of seeing this kind of distributions here, and it all depends to when you're actually visualizing your own data. And an interesting thing we mentioned in the beginning is that we were going to look at three things: histograms, binings, and density. And hopefully we're able to cover all three. Now, I mentioned before our session started that we'll be looking at projects, and the idea for all this is to ensure that at any point you want to visualize any information or stuff, you typically want to you know, think about a histogram and different ways. I think about numbers or distribution and different ways you want to look at it, in essence, in order to extract insights from it in terms of distribution. The essence of that visualization is to look at the way your data is distributed and to see if you can extract insights from that. Is it skewed? Do you have outliers? Right? What does that mean? Right? And it's interesting that how we went from just something basic, you know, to adding a little bit of parameters to it, and then, you know, realizing that we can also have them side by side, and then go on to have like a 2D side to what we have going on. All right. Do you have questions? If you have questions, please feel free to drop it in the comment section, or also indicate by raising up your hand if you're in the call, live in the call here. Or you can, if you're watching a recorded session, please drop a question and a screenshot in the Telegrams channel, and then we can start our interactions with that. Right. All right.